Thanks for the invitation. It's always a very nice conference. This one, sorry that I couldn't be personally there, but will try my best. So this is the last day and everybody probably is already a little bit tired. I'm going to give a talk which is very self-explanatory. And I wanted to tell you about what happens when we consider open quantum systems which are in contact with finite systems, finite baths, what is different in this case, and especially why this is important. So before proceeding further, I would like to, So I want to show you who are the really authors of this paper. This is work done in collaboration with Andreu Riera Campaign, which is now finishing his PhD in my group and moving soon to Innsbruck, and Philip Strasberg, which is a junior leader in our group at the University Autónoma of Barcelona. And I wanted to outline what we are going to do, what I wanted to explain you. First of all, I would like to show you what it's important to consider finite paths and why we care about that. And then I want to show you how we can describe an open quantum system which is dynamically evolving with a finite path. I want to show also how do they behave thermodynamically. So if we are able to recover a thermodynamical behavior which is consistent, and then I will leave some open questions. Okay, this work, it's based in these two papers that we have put this year in the archives. So this is the thing that I'm going to present, but it's based in the work of other people. In particularly, I wanted to put here, it's based on the works of Massimiliano Esposito and Gaspard, which they treated this problem already in 2003. And then later on, Breuer was reusing this problem again in 2006. And for some reason, and we believe that the reason is because they derive master equations which were a little bit limited use, this tool was not very well known. So what we wanted to do when we started to do that is to see how we can a little bit widespread this tool and see if this tool leads to thermodynamical consistent equations. And later on, well, it's also based in these things I will explain of observational entropy, which are the papers of Safran, Esposito, and Philip and Andreas Winter also. And there is a very nice application that has been appeared now on PRE, which is why thermal machines can be much more efficient than we thought if they are in contact with a finite baths. This is the reference aid. And I wanted to use this thing also to explain some of the problems that we encounter in cold gases. Okay, so what is all these things about? So if we have to have a motivation on how the thermodynamics has changed in the last centuries. So when we started, we had a very big sizes and very big environments. And then this the first thermodynamical experiments were just using that what is the change in volume and pressure, and then Boltzmann was already appearing here, although that was previous to him, saying that this very famous result of pressure and volume is related to the Boltzmann constant. But as the system size was smaller at the beginning of the next century, when it was all this Brown motion movement of individual molecules of a gas in a box in which they have this very random movement. And then already Einstein was showing that although the mean displacement of the particle is zero, the variance of the displacement of these particles is not zero. And this is also related to the Boltzmann constant and the temperature. And nowadays that the environment size is starting to be smaller and smaller due to this miniaturization of all these quantum systems that we know. So not only we are able to make systems which are very small, but also the surroundings are small. Probably the question is what is temperature, which is something that it's not very clear. So what is a finite bath? So finite bath has to require, so obviously means the system is finite, but what is different from infinite baths? So if we have a system, our system, in contact with an infinite bath, and we assume that initially they are separated, and then we allow the system and the bath, they are coupled. So we know that the result will be a thermalization. Okay, and at the end of this thermalization, the system will acquire the temperature of the bath, and the system and the bath will be uncorrelated again. Well, if we have a finite heat bath, what is going to happen, it's, and we leave the time go, it's that the system will also equilibrate, okay? But it's not going to equilibrate to the temperature of the bath. And the reason is because the system is finite, and although the weak it's coupling between the system and the bath, the exchange of energy between the system and the bath now affects the bath, because the bath has a finite degrees of freedom. It has to be a bath, so it has to have enough degrees of freedom, so that many degrees of freedom than the system, because if not, there will be two systems, so it will not be able to, we will not be able to talk about a finite bath. But we see that this exchange of energy, what it will make is to build correlations between the bath and the system, and it will be a back action and so on. And this is the kind of systems that we are interested in. So why do we care? So I'm going to put an experiment that we are trying to explain, which is completely different to these things. So this is work done a few years ago in the lab of Tillman Esslinger in ETH, in which you have two cold gases, okay, which I'm going to call it left and right. And here we are not talking about temperature, so it doesn't matter. We are talking about the number of particles. And then with a laser, one makes a channel between these two left and right systems. And so it makes a transfer between the left to the right on the number of atoms. And if you look how is the imbalance between the number of the atoms in the left and on the right, there is a moment that it reaches equilibrium. But this is a problem that in any case, I can consider that the small system, it's in contact with a system which is infinite, with a bath which is infinite. So the finiteness of this bath is really crucial to understand which is the physics which is behind. Another example that we are also interested on and working on is that we are able to explain, and we will see that in this framework, the concept of negative temperatures are thermodynamically consistent. They don't bring any problem. Okay, so we can explain thermodynamically consistent the experiments of Immanuel Bloch a few years ago, in which they were looking also in a finite system, the arising of these negative temperatures. Or we are interested, for instance, in measuring which is the temperature of an ultra cold gas when this ultra cold gas is a small, a fermionic ultra cold gas, by putting a thermometer. And so that we have to go out of this paradigm that we have a very huge system, but we have just a system of few fermions, which is not very huge, few, it can be hundreds of fermions, which is not an infinite system, and put a thermometer and trying to see which is the temperature, which is of the system. Okay, so how do we describe all these things? Oops. Just a second. Okay, so in equilibrium dynamics, the ones that we are normally doing, we know that we have a system bath, and the paradigm is that we have access to the degrees of freedom of the system. We know it very well, but the bath is very large, and therefore we don't have any access to and we are not interested. So how do we describe that? Well, we put that the bath is in a reference state, which is a given temperature. So we have our Gibbs state, and then we have an initial state, which is the system times the bath uncorrelated. And then we trace out the bath, and then we end up with an equation of motion for the system, which is this Liouvillean equation. This is our standard way of doing it. Okay, so, and we have some approximations to solve these equations. In the case of the non-equilibrium dynamics, so when the bath is a bath, but it's not infinite, and therefore it's affected by the system, the paradigm is a little bit different because we assume that we have a system in which we know the state of the system, and we have a bath in which we don't know maybe probably all the states of the bath because still is a bath, so it has many degrees of freedom, but we are going to consider that we have a coarse graining so that we can know which is the energy gaps inside of these windows. We have access with our experiments to measure which is some of the energies, so some windows of the energies of the gap or the energy of the bath on a coarse graining method. And when we do that, we know that depending on which is the energy window that we are testing, there is many states on that. Okay, and this is what we call the volume of the states. So now, in order to do our description, what we consider is that we have a normalized conditional state of the system, given that the bath is at some given energy E. Okay, so, and we stay, and I will explain a little bit what it's that. So our initial state, now it will be a correlated state that our system has, it's depending on which is the energy of the bath. Okay, so we have a projector PE, and then it's given that the bath is at this energy E, our normalized conditional state of the system is rho S of E. Okay, and this of course goes beyond the typical approximation because we have a classical correlation system here. So if my system is at a given energy, if my system is here, the bath has this energy. I will show you how it works. Okay, and then if I want to study which is this normalized state, I trace out the bath, and the total state of the system will be the sum of all possible energies of this conditional state of the system. And this is quite interesting because when we do that, one of the things that we see, okay, okay. By doing that, one of the things that we will see is that each of these rho S of E, it will follow a Markovian evolution, but the sum of them, it doesn't have to be Markovian. And we will see that indeed it keeps track of non-Markovian effects. So how do we do it? So we have this system and bath, which are weak coupled, so we are not interested in strong coupling. And then we derive a master equation. And this master equation for the system, it's a master equation which is conditional and which depends not only on the energy, but also on the dissipation rates, on the transition rates between the jumps that I can do between the system and the bath. And intuitively is that I have a dissipation rate which depends on the state in which the system is, and when it jumps, it will jump to another state of the bath also because it will change energy with the bath, okay, with some frequencies. So it's a kind of a master equation, which is a little bit more complex, but that it can be solved in a very similar way in which we solve the Bohr-Markov approximation. So what we do is that for each conditional state of the system, we use the Bohr-Markov secular approximation. Then we can also evaluate the dissipation rates or the correlation functions without having an explicit knowledge of the bath operators, because although we know that the systems are becoming and the environment is becoming smaller, and therefore we have more access to know things about the environment, but nevertheless, the environment is still an environment, so there is not need to know all the details. So without even knowing which are really exactly the form of the bath operators in the interaction, just by using kind of heuristic approaches, like it can be a random matrix approximation, or we can use the hypothesis to put some structure on the bath, we will get the results which are correct. And then the dynamics of the total system at time t is just the sum of the dynamics of each of these conditional systems at energy E. And as I said before, although each of these ones, maybe this is rho s, although each of them it's Markovian, the sum doesn't have to be Markovian. So let me show you with a simple example. So we use a spin two-level system, which is coupled to a structure environment. So it has just two levels, and we assume that the bath, it has only these 4 coarse graining energies. And we put a very simple system because we wanted to solve it exactly using a Schrodinger equation. Okay? And we let it evolve. And this is the evolution of rho s of E. So for a given energy when it's in the excited state. Now, so of course, what we can have is that this system decays, and therefore the bath it's in another energy. Okay? Because one of the things which is important here is the total energy of the system and bath. It's a conserved quantity, and this will be the key point to do thermodynamics. So if I solve that exactly using the Born-Mass secular approximation, this is the result that I get. So after some time, we know which is in measure which is inverse to the gap energy, the system equilibrates. But this is quite different from the exact behavior. And if we solve it with our equation with the ML, we recover quite well the exact behavior. Okay? And the reason is again that the system is finite, and therefore the fact that the bath is finite, so and it has a structure which is clear, and therefore there is always an exchange of interaction when they are in contact between the system and the bath. And it's not correct to assume that the bath doesn't change, which is when the bath is infinite, it's correct. When the bath it's finite, this is not correct. Okay, so let's see a little bit how is the thermodynamics when we do that. And well, again, what it's very important to say is that we have that the energy of the system plus the bath, it's constant. Okay? So imagine that in order to try and to see how is the first law of thermodynamics, and in order to put a kind of inject some work there, we have to drive our system, okay, slowly, okay, and to put some power on that. So what we are going to do is that we will assume that we have now a system in which is periodically shaken with very slowly, so that it's a two-level system, that the high energy level can change as a function of time. And the dynamics, and then we will look how is the dynamics of the system, and then we will see that, of course, the system is shaken like that, but when the system falls into the ground state, necessarily the energy of the bath increases. Okay? And then when we look which is the internal energy, okay, of the system, we recover that the change of the internal energy that can be breaking in the correspondence between exchange of heat and work, and the first law is fulfilled. Now, if we want to talk about the second law, we have to talk about entropies, and then, well, as the people who is working on that, you know that the entropies are a very difficult thing to understand and to define, okay? And especially when one wants to put a coarse graining. So we can talk about entropy, first of all, in the typical statistical Shannon entropy. So assuming that we have a state, so we have our space, and we imagine that we coarse grain this space into cells in which we want to know which is the state that we have, which is the possible state, and which probability it is. Okay? So if we do like that, so we associate with some probability P00 that the state is on the cell 00, or P13 that the state is on the cell 13, or for instance, in this case, we will talk about this for Newman entropy. Okay, and now we can talk about this this Shannon entropy, which is the same, which is the sum of the probability, okay, minus log of p. So if the state is in a single place, we know, see, our state is C, we know that since everything is known, the probability is 1, okay, the entropy is 0. But if we have a combination of possible states, then we know that the statistical or the Shannon entropy, it's just log of the sum of the probabilities, and this is different from 0. Okay. We can also talk about this microcanonical or Boltzmann entropy, which is a little bit different. So we distinguish between, for instance, our phase space between left and right. And now what we look, it's how many cells they are in each of these divisions. Okay? And in this way, when we look at the microcanonical entropy, we find that this is proportional to the number of microstates which are possible in each of these divisions. Okay. So, and we will try that the microcanonical energy depends on the log of the volume on the configuration I, so how many states I can have in the blue area, on the left area, and how many states I can have in the right area. Okay. So if we want to talk about now observational entropy, in which we have that we don't have a complete knowledge about the system. So let me say it again. So, but we can have a coarse graining of my phase space energy into the left and into the right area. Then we have to define what is this observational entropy, which is a very old notion, which is a notion which was already introduced by von Neumann almost 100 years ago, which is the entropy that I really have access, that I can look at that, okay? Because obviously I cannot see all the microstates in the all possible microstates which are in one of the configurations, but I have access to that. So the observational entropy, then it's defined like the probability divided by the volume. Okay, so this is the log of p plus log of the volume which is accessible. Okay, and this is what we are going to use. So I can have the observational entropy that I'm going to be on the left or on the right will depend on how many microstates it is, and it will be a coarse graining effect. So, and since we are using a coarse graining for the energy, in which we assume that we have an estimation, which is the number of microstates that we have in each of the shells of the energy, now we have to do the same in order to build the second law of thermodynamics. And when we do that, well, we know that the second law of thermodynamics tells us that the total entropy of the universe can increase as a function of time. And now when we look at with this observational entropy, we find that the total entropy corresponds to the total entropy of the system, to the total entropy of the bath, minus the mutual information between the system of the bath. Okay, and this is always like that. So on this, now we wanted to show how these results hold using the M, this equation. Okay, and then moreover, we can use Clausius inequality, which Clausius inequality is an inequality that shows that when a system in equilibrium absorbs heat or energy, its entropy increases by a quantity which is equal to the heat that absorbs divided by the temperature. So normally this Clausius is assuming that we have a finite temperature, a constant temperature, which is the temperature of the bath, okay? And it makes the link between the first and the second law. But when we put here the Clausius inequality, what we realize is that the correct way to put the Clausius inequality here, it's that during the transformation, since the bath, okay, so we have our system interacting with the bath, and along the time it's evolving, the bath it's evolving, and therefore its temperature it's evolving. So if at each instant of time, we are able to associate to the bath, a given equilibrium state to a non-equilibrium temperature, okay? So we take the state of the bath and we associate it like if it was a Gibbs state at a given equilibrium, T star, and then we use this effective temperature, which is a non-equilibrium effective temperature because the bath is not in a Gibbs state. Then if we write our Clausius inequality, it will be like that. And the second law, which connects the first law, because it's the absorption of heat, with the second law, which is the entropy, will hold like that. And this is maybe one of the things which is nice, which is this deriving a temperature, which is a non-equilibrium temperature, whatever that means. Okay? So let's see how are these results. And when we look at the results, so we take the same system that we were taking, a very simple system, and then, okay, which is this spin coupled to this structure environment. And I want to go a little bit slow as a function of time on showing this graph, because probably it's the most important graph of our results. And first of all, I want to show, so this is a system which is driven periodically with a small drive. And so, and here we start by this blue line, and this is the entropy, observational entropy, as a function of time. And we see that this blue line, which is the observational entropy as a function of time, behaves as it should behave, okay? So it increases, although it increases in steps, and these steps are related to the driving of the system. And then we have this green line, which is the sum of the observational entropy of the system plus the observational entropy of the bath. So here we are ignoring the classical correlations between the system and the bath. And this is the difference between these two plots. And the orange, of course, it's bigger than the blue because we are adding here, which is the entropy increase of the bath also. And finally, the green line shows the Clausius inequality, okay? So that the Clausius inequality, when we fix that our bath, calculate which is this effective non-equilibrium temperature, is always larger than the observational entropy always of the system. And on the inset, we show how is this non-equilibrium temperature. So we start with, it's an academic thing, so we start with the temperature being 0, but then the temperature, effective temperature of the bath increases, then we are shaking, this is a lot, and the effective temperature of the bath decreases. So how is this M when we see like that? So we see that we are able to see things for a finite bath, which are better. But of course, we can say how far this is from the typical master equation that we are used. And I will finish with that. So when we work with the M, we are able to find a hierarchy of master equations. So the first master equation is that assume that I have all knowledge about the environment of my bath. All dynamical information is included in the system. Then I know that the evolution is unitary, because it will be like if it was a closed system. I know absolutely everything of the bath and I know how is the change. Then the second step, so that will be this big kind of evolution. The second step is imagine that I have an open system that it's allowed to exchange energy with some probability, okay, with its environment. This is the M, the extended microcanonical master equation. This is the equation that we have been working with that. Then if we go further and we say, well, maybe this is not needed. In some cases, it is enough that we have a bath average energy, okay, in which there is this exchange between the bath and the system, but only on average, okay? So this is, then we recover Born-Markov secular approximation in which our system, it's an effective non-equilibrium temperature, which changes on time. Okay, it's a dynamical thing. And finally, the typical Born-Markov secular approximation is that we have a system which is invariable, which is at a fixed temperature, V zeta, so the inverse of the temperature, and it doesn't change on the time. So this will be how one goes from infinite path system to a finite path system. Well, I have shown, which is, I'm going already to conclude. I just wanted to see that we know how to describe this open system dynamics. Of course, the more complex is the description of the bath. So the more accurate is the description of the bath, more complex is the master equation. So there is an equilibrium. So in order to be a master equation that you can use for many things, you have to have a description of the bath, which is, it can be done with this coarse graining, and you can put for the bath a lot of approximations. So you don't really need to know exactly how is the bath. Okay? And we have seen that by doing that, which is important, you can recover all the thermodynamics out of equilibrium. Okay, so because the system, when it's exchanging energy with the bath, of course they are not in equilibrium, but you recover the first and the second law, and moreover you recover Clausius, and this kind of non-equilibrium temperature have some consequences which are quite relevant, and this is the work that Andreu, Philip, and Maria have been doing on paper, which originally was resurrecting Clausius, but the editors didn't like this name. And so now it has a more formal naming, which shows that using this approach, the efficiency of thermal engines when the bath is finite can be higher than it was thought. And it's a very nice paper. So let me just conclude with saying that, of course, not always, but sometimes, and we believe that more and more, because the quantum systems are being getting smaller, and also the environment it's keeping smaller. So then taking into account that these finite bath properties, it's crucial to understand the physics, and it will give us a physics which is better than the one that we know. So for instance, one of the things that we are working now and that we tried, it's on extracting which is the temperature of a bath of fermions, okay? And the thermometer, you need a thermometer, and the thermometer doesn't read the temperature. So it's reads a temperature which is a non-equilibrium temperature, and then you have to extract it and see which was the original temperature, because it changes the fact that it is. And well, we have shown that this master equation, and we have shown that you can, we recover kind of a thermodynamical approach. And with that, I will thank you for your attention. Thank you very much.
Questions from the audience first? Tak, okay. Please.
Hello, Anna. Thank you very much. Paweł Hrodecki speaking. So a very naive question, because first, how to define temperature in the situation, you know, the concept of temperature should be a little bit different here, right? So how is it kind of intuitively defined? This is the first question. And the second is, you know, originally temperature was a single parameter because the only knowledge was just the mean value of the energy, right? Here, there is more information. So, so the first naive, you know, intuition would be, okay, there should be something like not one temperature, one parameter, but, you know, something extra, maybe two parameters, you know, maybe. So that's my question. Thank you.
Yeah, you are completely right that when you go to this limit and when there is exchange and you don't have only the average energy of the bath, the question of temperature, and this is what is temperature? This is a very good question. So the only thing that we know at this moment is that we can associate a temperature which depends on time, because there is exchange of energy between the bath of the system. And in order to define this temperature, which we call it non-equilibrium temperature, okay, the only thing we can do is that we associate that whatever the bath is there, okay, we map it like if it was a Gibbs state, okay? But of course, it will have for instance, this is the reason that I'm saying it's not a problem to have, it's thermodynamically possible to have a negative temperature, because that will be that the bath has a distribution of energies which is inverse of the usual. Okay, so it will not be a Boltzmann distribution, but it will be an inverted Boltzmann distribution, and this is possible. This is not a problem because it depends on the interaction. So it will have effectively negative temperature. So this is a fantastic question, and we know up to this point. Okay. That was one, no? And the second was? Yeah, you were saying that maybe one needs, now I remember, more than one parameter. I have to say that I don't know.
Right. Yes. They took microphone from it, so I couldn't. Yeah, so that was the more parameters. Yes, exactly.
Yeah. Yes, I don't know. I know that you can always play this game of saying, imagine that the bath was thermal, which will be the temperature, but that changes. Okay, so it's a temperature that changes. That's the reason that we call it non-equilibrium temperature, but it's a complex thing to know what it's temperature and what it's entropy, as you know. Yes.
I see. I thought that maybe the delta of energy is kind of the extra parameter that might have been built, but I don't know how actually.
But it is related. There is a question here I see from Klaus saying, how is the role of measurements? Well, the role of measurements, it's clear. So this is the second paper that we did, because at the end you get information by measurements. So in this first paper and the one that I was explaining, we assume that our measurements are projectors, because that's a little bit easy to treat it. But then we were assuming that, imagine that you have imperfect measurements, which is normally the case. So instead of having projectors, you have a POVM, and then you recover. So you derive the MA with these more realistic and imperfect measurements. It's quite similar. So you have some differences, because of course with projectors you have more information, and with the POVMs, and you have to put some uncertainty. So you assume that you have a Gaussian distribution or something like that. So we were working on that in this second paper. It's important, but the structure of the MA is the same.
Thank you very much.
It's an odd thing. It's not. I wanted to tell you that it's an odd thing that comes from the works indeed of Svanchik Nakajima in the 50s.
So
okay, thank you.
We'll give you a chance of participants online, so further questions. Okay.
Yes.
And we have an online question.
From the
An online question.
Online.
Yes. This is exactly what we are trying to do right now. When I was telling extract this non-equilibrium temperature experimentally. Yes, because this is what I was telling you. For instance, if we try to do thermometry, okay, so imagine we have our system, we want to know the temperature of a finite system. We put a thermometer, which is a sample, okay? And now the sample is small, so we cannot assume it's a infinite path. And now we look only on the thermometer, which is the sample, and we obtain some temperature. This temperature, it's a non-equilibrium temperature. Okay, so we see it depends on the time, and then at the end, these are preliminary things. We see that it reaches, because it equilibrates, all right? Even if the system is finite, at the end, the system equilibrates, but equilibrates at the temperature, which is not at all the temperature of the bath. And this is what you read. So, but you see how is the dynamic. So you are extracting, pam, 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 pam. See, you can do it. I think theoretically, experimentally.
Thank you very much. I think we can, we must finish the discussion, and thank you again, the speaker.